Alright, so this is the lecture for Chemistry 110, and we're starting Chapter 2 in the book, and it's more on gases in the atmosphere, and we're going to look at the ozone layer. Now this is a nice picture from your book, and shows arrows coming from the sun, and that represents sunlight. But notice that as the arrow goes through this sort of layer here, what happens is the arrows get diminished, and it's a representation of what happens by this thing we call the ozone layer. It's above the earth. It limits some of the sunshine coming from the sun hitting the earth, and specifically it's the highest energy light. It's called UV light, and we'll get into what UV is eventually. But we will look at the chemistry of this protective layer on the earth. Okay. What is the ozone layer? A protective layer in the atmosphere over the earth. It's not at the surface, it's way up high, so we aren't subject to it. What's ozone? We'll get into that. We got to get into predicting structures of atoms and molecules. We did molecules already in the lab, but we'll get into then not only that, but how molecules interact with light in the CFC problem. Here we go. Okay. How is ozone made? Well, it turns out that when you've got oxygen, and we have lots of oxygen, 21% of our air, and there's some high energy process, like a lightning strike, like high energy light bulbs, like the car engines, or even just lots of sort of heat and energy and pollution in the air, you can generate what's called ozone. It has a sort of a thick, sweet smell. When you smell rain coming, it's because the lightning in the rain clouds has made enough ozone that you can smell it. You smell it at 0.01 parts per million, and the interesting thing there is that's too low a concentration to actually hurt anybody. So we can actually smell it at a concentration, for example, from a rain cloud, that's too low to actually hurt us. But it can hurt us in higher amounts. In anthropogenic sources of ozone are the oxygen that mixes with sunlight in polluted air in cities, and that can build up enough to be harmful. And what it does is it lowers lung capacity. It hurts your lung tissues in such a way it's almost like having asthma. You can't get enough air. And there are curious other applications. I'll bring up one. If you bubble ozone through water, you can purify the water. It'll kill off the bacteria, and that's an interesting thing as well. The one thing on here I haven't checked is stratospheric ozone, so that's a different animal. It turns out that the sunshine has much higher energy light in the stratosphere, the layer that starts at about 15 kilometers above us and goes up, and there's a layer of ozone created up there, and it is actually not harmful. It's extremely beneficial. It protects our world. Okay. Now, this is a good time to bring up the topic of allotropes. It's a good chemistry topic, and you hear the word allotropes coming and going. Oxygen is made out of oxygen atoms, and it's diatomic. We're forever writing it as O2. Ozone is the element oxygen too, because it's got all oxygen atoms, but it's got 3 of them linked together. Oxygen and ozone are allotropes of the element oxygen, because they have different molecular structures, even though they are still made of the same atom. So they still are the element oxygen. To illustrate this, I've got this guy. He's a coach, famous basketball coach with a famous temper. And so to illustrate the difference, I've got him breathing oxygen, and then I'm saying that this is what he'd look like if he was breathing ozone. Other famous allotropes I'd like you to know about. Carbon can be in 2 molecular forms, and they're fascinating. One is the diamond, the other one is charcoal. All right, they're both pure carbon, but the molecular structure is different. We'll call the 2 allotropes of carbon diamond and graphite. And I'm a little bit out of date here because there are actually some new allotropes of carbon that I haven't put in there, but I'm going to let that go for now. Phosphorus is another famous one. You can have that molecular structure or that molecular structure. This one gives us red phosphorus, and it is found in the matches when the striking surface. And then this one's called white phosphorus. I didn't have to write that there. Here it is here. Here's white phosphorus. And I didn't have a good thing to show you, but this is an example of white phosphorus. If it comes in contact with air, like in this container, it spontaneously bursts into flame. So completely different than red. It's a different color and much more reactive. Those are allotropes. Okay, so time for a pure chemical topic. How can two oxygen atoms have two molecular forms? We actually saw that. We did Lewis structures, so we saw the rules for putting molecules together. But what we skipped early on was atomic structure, the rules for making atoms before you get into this. So we're going to do that a little bit here now in this lecture. Okay, first of all, many years, many experiments. The history is absolutely fascinating about taking these indestructible atoms and subjecting them to a lot of high energy processes and realizing that what would fly out of every single atom were negatively charged. Whoops, didn't want to do that. Were some negatively charged particles and also some positively charged particles. And in our lives we see this property of negative and positive charge every time we run into a static electricity sort of thing, like if you rub a balloon on your hair and it sticks to a sweater. It's because there's a charge on the balloon that's negative, a charge on the sweater positive. Well, it became apparent looking at different atoms that this property of negative and positive charges come from atoms. Every atom has negatively charged particles, we call them electrons. Every atom has positively charged particles, we call them protons. Now the properties of these things are that pluses always attract minuses, okay? And it's also true that minuses always repel each other, a fundamental fact of nature. Neutrons are another particle, and they have no charge at all, so they're neither attracted to nor do they go away from the charges ones. Now, an interesting property is that we can actually measure the mass of these things. And the reason it's interesting is it's something like 10 to the negative 16th kilograms. It's so unimaginatively small that we absolutely can hardly even think of this mass. But we have machines, they're called mass spectrometers, that can measure the mass down to 10 to the negative 16th kilograms. Now we find protons and neutrons as the same mass, and we find electrons as about 1/1000th of that mass, so it becomes convenient to define a new unit of mass. It's abbreviated AMU. We will call this the atomic mass unit. So a proton weighs 1 atomic mass unit. That's how it's defined, the weight of a proton. And the mass of a neutron is 1 atomic mass unit. By happy coincidence, neutrons and protons have the same mass. Now, electrons have a very much tinier mass, and we are going to tend to ignore their mass. We are going to tend to think of them as though they have no mass at all, even though we know they have a little tiny bit. Okay. Now, if every single atom you come across in the periodic table, it turns out they have different numbers of protons, neutrons, and electrons. So let's look a little bit at how we get to these things. First of all, in every square on the periodic table for an element, the number with no decimal point, it's an integer, it's just a counting number, will always be the number of protons. We'll call this the atomic number. It's always the number of protons. Now it tells us something about electrons too. It tells us the number of electrons only because for every single proton in an atom, it usually has an electron. They're usually the same. And for that reason, the atomic number is the number of electrons. But it has to be the number of electrons in what we call a neutral atom. If we were to draw an atom and it had a plus charge on it, it means that the atom is missing an electron. because it has a plus charge that's not matched with a negative. So in this case, C plus, we'd have 1, 2, 3, only 5 electrons. But in a neutral atom, one with no overall charge, the atomic number is the number of electrons as well. Each atom has its own atomic number. Okay. Neutrons. Well, that's a little trickier. Let's do the neutron thing here a little bit. If we take the example of carbon, we can take carbon atoms, and with our fancy machines, it's called a mass spectrometer, we can measure we can measure things about the atom to tell us how many protons, neutrons, and electrons we've got. Interesting. Carbon has 6 protons in every single atom. It has 6 electrons in every single atom if it's neutral atom. Let's say they're all neutral. But it does not have the same number of neutrons in every single atom. Some atoms have 6, some have 7, some have 8. So, what we say is that carbon has 3 isotopes. Isotopes are the different atoms of an element that differ by the number of neutrons. We've got ways of writing these things. You need to know this too. Carbon 12 has 6 protons and 6 neutrons, so the 12 means the protons and neutrons added together. Therefore, carbon 13 is what we call 6 protons and 7 neutrons. 6 plus 7 is 13. Carbon 14 is what we call 6 plus 8 neutrons, because 6 plus 8 is 14. They have somewhat different masses as well. They have 12 atomic mass units, 13 or 14. In fact, these numbers are often called the mass numbers because they're the same as the mass in AMU. Okay, now through lots of experiments that I don't have time to get into, we find that the atom has its protons and neutrons stuck in a little tiny point in the middle, and we're going to call that the nucleus. You need to know what the nucleus is when we're in an atom. It's a point in the middle, contains all the protons and neutrons. The electron cloud is a part surrounding the nucleus, and it contains all the electrons. Now, it's interesting to note that the protons and neutrons carry almost all the mass of the entire atom, like 99.99% of the mass. So all the mass is in a little tiny pinpoint in the middle, and a tiny, tiny amount of mass is from the electrons floating around on the outside. Atoms are mainly pure space, believe it or not. Okay, now here's a little exercise that I ask you guys to do sometimes to tell me that you understand protons, neutrons, and electrons. Let me run through it real quick. Here's a picture of an atom, and if I ask you, gee, where are the protons, and put a positive charge on the protons for a carbon atom, you'll look on the carbon periodic table, you'll see 6 is the atomic number, and you'll put in 6 because protons are in the middle. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Now you know in the middle there are also neutrons, and so the rest of them have to be neutrons, right? And you know the things surrounding on the outside are electrons. And so what you'll do is you'll say, okay, I know what this is. This is a carbon, because it's got, well, I told you it was carbon, but it's carbon, and the protons and neutrons in the middle add up to 14. So this is carbon 14. Okay. The charge on the atom is how many pluses you've got. 1, 2, 3, 4, 5, 6, minus the number of minuses you've got. In other words, if you have pluses and minuses equal, the charge is 0. Now, on the other hand, if you were to be missing a minus, you only had 5 out here, then the charge would be plus 1. And if you had a minus there, but you had an extra minus in there somewhere, the charge would be minus 1. Pluses and minuses cancel each other out. Whatever's left over gives you the charge on the atom. In this particular atom, I'll cross off all the stuff. The answer is 0. The atomic charge is 0. Okay, here's an exercise. I'll let you do that if you want to do that. Okay, and now we got electron configurations, and here's where I'll stop because in fact we did this in the laboratory, so I'll just let the laboratory be the exercise. on electron configurations.